The Hantzsch dihydropyridine synthesis is a one-pot condensation in which two equivalents of a beta-keto ester or a 1,3-dicarbonyl compound react with an aldehyde and ammonia to produce 1,4-dihydropyridines. This reaction was first reported in 1881 by the German chemist Arthur Rudolf Hantzsch. The product of the reaction is a symmetrical 1,4-dihydropyridine, which is formed in good yield. Such product can be oxidized to the corresponding substituted pyridine by, for example, nitric acid or iron-free chloride, although the oxidation is spontaneous in some cases. An interesting fact about 1,4-dihydropyridines is that some derivatives shown on screen are used as calcium channel blockers acting as anti-hypertensive drugs. For the synthesis, I'll be using two equivalents of ethyl acetoacetate, benzaldehyde as the aldehyde, and ammonia, while ethanol will be the solvent. The product obtained will have a phenyl group in position 4, which comes from benzaldehyde, two methyl groups and two ester moieties coming from ethyl acetoacetate. The chemicals needed for the reaction are 12.07 grams of ethyl acetoacetate, 4.93 grams of benzaldehyde, about 4 milliliters of 23% aqueous ammonia, and 10 milliliters of 99% ethanol. I start by weighing the ethyl acetoacetate in a 250 milliliters flat-bottom flask. I then weigh the benzaldehyde. Mine is a bit yellow, but that's not a problem. I then pour the ethanol and add the ammonia. I set up for the reflux. I use some aluminum foil to provide a bigger heating area. I add a stir bar and on top of the flask I connect the alien condenser. After the stirring and heating are switched on, the yellow mixture starts refluxing. I let it reflux for an hour, even if it would have been better to let it react for a longer time. What's happening in the flask in terms of mechanism? Let me explain it. The Hantzsch dihydropyridine synthesis proceeds through two intermediates, the alpha-beta unsaturated carbonyl compound and the enamine. In the first step, ethyl acetoacetate put into solution forms the enol by a process called enolization. The enol is a nucleophilic species, therefore it can attack an electrophile, in this case a molecule of benzaldehyde. The compound produced easily dehydrates, forming the first important intermediate, the alpha-beta unsaturated carbonyl compound. The reaction described thus far is known as the Knoevenagel condensation. In the second step, another molecule of ethyl acetoacetate is attacked by ammonia. This time, the ethyl acetoacetate will act as an electrophile because of its carbonyl group. By losing a molecule of water, the amino alcohol forms the enamine, the second intermediate in the Hantzsch dihydropyridine synthesis. The nucleophilic enamine will attack the alpha-beta unsaturated carbonyl compound at the beta carbon to generate a new molecule, which undergoes a proton transfer and two tautomerizations, reforming the enamine and ester moieties. The nitrogen atom of the enamine closes the ring by bonding to the carbonyl on the other side of the molecule. After a final dehydration, we are left with the final product, the 1,4-dihydropyridine. An hour later, the mixture assumed a darker yellow color. I then take away the hot plate to stop the reflux and let the flask cool to room temperature. In the meantime, the product has started crystallizing. I placed the flask in an ice bath, add 10 milliliters of water, and with a metal spatula I break the clumps of crystals. While the content of the flask is cooling down, I set up for the vacuum filtration. Once the mixture is cold, I dump it into the Buchner funnel and filter it. I wash the flask and the crystals with about 10 milliliters of cold water. In the filtrate there are some oily drops, probably a decomposition product. This is the crude product. For the recrystallization I use in total 75 milliliters of 95% ethanol and 15 milliliters of water. Since it was my first time doing this, it took me a while to figure out the quantity of the solvents needed. In addition, the dissolution of the compound is quite slow even at high temperatures. A good stirring makes the difference. Once a clear solution is obtained, I stop the stirring and let the product slowly crystallize. The beaker with the crystals is placed in an ice bath, and again the product is vacuum filtered and washed with cold water. The dihydropyridine is left to dry overnight on a paper towel. Here's a picture of the dry product. It weighs 8.60 grams, which represents a 56% yield based on ethyl acetoacetate. Since it looked quite yellow and had a faint smell of benzaldehyde, I decided to run a secondary crystallization. This time I use 50 milliliters of 99% ethanol and 10 milliliters of water. It's not shown here, but after a clear solution was obtained, I added another 2 milliliters of water to further decrease the solubility of the compound. As before, I filter the crystals and wash them with cold water. After drying, I obtain the pure dihydropyridine. It weighs 7.67 grams, which represents a 50% yield based on ethyl acetoacetate. It's way less yellow than before and has no smell of benzaldehyde. I obtain another 1.61 grams of recrystallized product from the various filtrates. An interesting property of some 1,4-dihydropyridines is their fluorescence under UV light. I took some pictures of the crystals under the microscope using long-wave UV light. Leave a thumbs up and a comment if you like the video, any feedback is welcome. Thanks for watching!